Right. So today we're going to start, which is the end of the Fourier material or the spectrum content stuff. And we're going to talk between today and tomorrow about something called a Bode or Bode or Bode plots. Sometimes we just say Bode plots in being Trinidadians and so on, like how we say, instead of Nestle, we say Nestles. Anyway, so right, so we're starting on this topic. The other topic after this would be on stability, and that's one. I have some pre-recorded lectures that I'll let you look at that during the course of the week, and then we'll meet to discuss as we go forward. All right, so we're in the sort of final stretches of the course right now. I haven't started to mark this in course as yet. I've started to mark the electronics, and people are doing reasonably well, and I'll tell you more about that this evening. All right, so let's see how that goes. Okay, so as usual, if you have any questions at any point in time, feel free to try to catch my attention and ask. If you put the chat on, I have another computer here, but it's difficult to watch both computers at the same time. So if you do put something on the chat, may make some sort of attention getting sound, and I will try to come across and address the situation, all right? Okay, and if you're not hearing me for any reason, let me know. So, okay, we have been speaking about the transfer functions, frequency transfer functions, and so on, and we had reached a stage between here and sort of, interestingly enough, as we were paralleling it in the electronics course for those of you doing it as well, that we saw that if you were given something like this, a transfer function for something, we do not know what that something is, but if you were to ask, be given a question, well, what is the magnitude versus frequency of that transfer function? In other words, G of J omega, what does the magnitude versus frequency look like? And what does a phase versus frequency look like for it? Well, we know that the sort of initial step would have been to wherever you see the S, right? You take the S and you replace it with J omega inside of here, and then you get a function which is G of J omega. Okay, so to evaluate this, of course, when you substitute G of J omega in there, you could get this sort of behavior looking like, you'll see why I factorize it in a second. And then the next step, of course, if you didn't know anything else, would be to take omega here now, and of course you let omega go from let's say 0 DC up to some high frequency. We have no idea where it will stop, but you pick some values of omega between 0 and for argument's sake, let's say 10 megahertz, right? This is just for argument's sake. So you put omega in here, so you put omega in naught, and then see what J omega looks like. And then from there, you would be able to take what the magnitude of G of J omega would look like. And then you could also get the angle of G of J omega. Right? And when all is done now, you put a graph, you put all the omega values here, and then you plot the magnitude of J omega, and you get something, and then you make another graph, omega, and then you plot the argument or the phase angle of J omega, and you see what it does. The thing about it, of course, this is, yes, you could do it, and this is how, if you really want an accurate answer, this is how you have to do it. The problem, of course, is that in many times, or in many instances, and we've made the point before that what you can do is to, because it's a course where we're looking to, or it's an approach that we're taking and we're doing models, if we can find an idea how the model behaves, then we may not necessarily have to do a fully accurate plot of the response. So if you went back here, for instance, already we know if I were to ask you what was the initial value of this, you could use the initial value theorem. And if we wanted to know what was the steady state value of G of S in response to a step input, you could use the final value theorem. So in the time domain, you could get a lot of information about G of S without going to find the inverse transform and substituting values of T and so on. So we're going to take the same sort of approach here. Is there some approximation that we can do that will let us know how G of j omega behaves without necessarily having to substitute 10, 15, 20 values of omega and see what happens, all right? And this is in fact what, where this thing called an asymptotic plot comes in. It just so happens that a telecoms engineer at Bell Labs many years ago, Bell Labs are one of those telecommunication research facilities that have come up with and have invented any number of the communication technologies that we use. And in fact, an engineer who used to work, a lecturer who used to work in our Department of Electrical Engineering, somebody by the name of Professor Patrick Hussein, he's actually on campus in FST and may rejoin us at some point in time. He had worked at Bell Labs for many years. And in fact, he has, 30 or 40 patents related to telecom stuff. Henry Bode, or Bode, I think is how they really pronounce it, but however, just for our purposes, Henry Bode developed a process where instead of drawing the plot in this form by having to substitute a set of values of omega and plot one by one, he decided, well, wait a minute, we could probably approximate this by using a series of straight lines. So depending on what the straight lines do, if I could get it in a form where I could approximate the response by using a series of straight lines, then at least I can see, I could get an idea of what the response is looking like, and then decide if I need to go and substitute the more detailed individual values of omega. Okay, and from this, if you use the asymptotic Bode plots, we get two plots out of it, which is what we want, a gain versus frequency and a phase versus frequency. And what we're going to spend over the next few lectures is to look at the sort of how you develop it, develop the process for doing it, the sort of rules for drawing it. We already met some of that for those of you doing the electronics course last week when we were talking about filter responses and so on. So some of this will be a little bit of a revision for you as well. The first thing about it is that we plot the magnitude plot on a log scale. First off, we plot the amplitude part in decibels, and we plot the frequency response in a log scale. So if you look at here, the log scale is that each linear part here is actually 10 times the previous space. So this is 10 to the naught, which will be 1. This is 10. This is 100. This is 1,000. This is 10,000. The next stop would have been 10 to the 5th. The next stop would have been 10 to the 6th, and so on. But you notice in a reasonable state, in a reasonable space, for instance, a typical sheet of paper, I could go from 1 hertz to 10 to the 6 hertz or 1 megahertz by using a log scale. All right. So the two axes, that's the first thing. That the frequency axis uses a log scale. And as we mentioned before, anytime you have two frequencies here and here, where this frequency is 10 times this one, we call that a decade. So any interval, any frequency interval where the upper bound is 10 times the lower bound or the lower limit, you call that span a decade. So by using a log scale, we actually plot the frequency scale in decades. All right. Those of you who do music may have come across one called an octave. Don't know if any of you all play music and you come across an octave. An octave are when two frequencies are twice apart. So if I was plotting 1, 2, 4, 8, 16, 32, for instance, those sort of things, This span, these spans are octaves. Okay, and in the music world, and for people playing music and musical instruments and so on, you all would be accustomed to dealing with something called octaves. Okay, the decade is just a little bit broader than that. So an interval that is 10 times the span of the interval, the upper limit is 10 times the lower limit, is what we call a decade. Similar for the phase angle, we plot the phase in degrees. All right, so it starts, the middle is 0, and we go up to plus, sorry, this will be minus 180, and this will be plus 180. All right, and you already know that minus 180 is an inversion. So if something goes in like this, and somehow it comes out looking like this, this is a phase change. Depending on how you time it, this could be either plus or minus 180 degrees. It's inverted. All right. So and you know that already. The minus sign would come, for instance, if we started off and slowly the wave, we were measuring time this way. So the other wave started so, and then eventually so. So at this point in time, right, we move the 0 point here, right? So we've moved minus 180. If we had gone the other way, it would have been plus 180. But for a sinusoid, you really can't tell just looking at the sinusoid if it's a plus or a minus 180. All right. Everybody following so far? If any questions or if something that you observe you want to ask, now is the time to do it. Okay. Right. So let's look at this, and we'll come back to the decibel range in a little while. So the first thing is, of course, let's look at some example transfer functions, and we will use the example transfer functions to fill out the Bode or Bode diagram as we go along. The first sort of basic transfer function is one where the transfer function is just a gain, a constant number. So you have, let me get back my red pen here. So you have a system, this is HS, but the transfer function of the system is a constant, 10. So whatever goes in here, if X goes in here, you get 10X coming out here. That's all it is. So what is the magnitude versus frequency of that? Well, the magnitude of this, first off, Hj omega will also be K. The first thing that you do for frequency will be to get to replace S with j omega. H or j omega is also K. And what happens as I vary the frequency with that? Nothing, right? If I were to plot this, the magnitude of that remains that constant. And similarly, what about a phase? If K is positive, a positive number has 0 phase. A negative number is minus K, so that's 180 degrees out of phase, but it is also a constant. Yeah? So if I were to plot that on our, well, that's the first thing. So first off, the magnitude is constant. The phase is constant if K is positive at 0, or if it is negative, it is constant, but at minus 180 degrees. We're going to plot that in a second. The other thing is this unit, the decibel. And we mentioned that before, and you should have met it elsewhere already. To express something, the absolute value of something in decibels, you take the absolute value of it and you multiply it by 20 log to the base 10. All right? So any number that you get to convert it to decibels, 20 log 10, and we met that already a couple of times, you get the magnitude. So 20 log to the base 10, that's important, converts it to a decibel. And well, we mentioned that we're using decades for the frequency range. So therefore, if I were to plot the magnitude response for our first example, where the transfer function is just a gain, the magnitude response is a constant, right? And this would be in decibels, so it will be 20 log of K, whatever K happens to be, and the log scale is going on. Remember that this is going on decades, so 10 to the naught, 10, 10 squared, 10 cubed, all the way up, right? Just a constant. And then the phase is 0, because number doesn't have any phase angle. If it is a negative number, then then the phase is minus 180. All right, so either way, it will be either the magnitude will be at 0 degrees or minus 180. And again, it's just a straight line. Yeah, makes sense? Everybody okay with that? Nice. Okay, so let's start now. So that's the first one. The second example now, let's have a transfer function that has a simple pole at the origin. So the transfer function is K over S. How you know the pole is at the origin is that if you look at the denominator here, right? This, to solve this, S equal to 0 is the solution for that part. Just like how if I had 1 over S plus A, right? This place, at what point is S is equal to minus A would be the location of the pole for that particular point. Here, this is S plus 0, if you like. Right, so we have a pole at 0. So what is the magnitude and phase relationships going on here? Let's look at the magnitude first. We substitute S, we replace S with j omega again. So we get K over j omega, which is a complex number. The magnitude of the complex number is simply K over omega, and the angle is 1 over j, which is minus 90 degrees. Let's express this K over omega bit in decibels. In decibels, that is going to be 20 log to the base 10. When you see this, understand that this is base 10, okay? 20 log to the base 10 K over omega, which is this here, 20 log K minus 20 log of omega, right? Simple log behavior. We plot it, and we're going to get a line that is sloping, that has a negative slope. If you look at it, this is what we have here. And the thing now is to figure out what the slope of that line is. We inferred that last week in the filters class when we were talking. For those of you who were doing that. But let's see if we could figure out what that is, right? When, go to the next slide, when omega is 1, we're coming back here. When omega is 1, we have 20 log K. If omega is 1, log of 1 is 0, so we have minus 0. So at omega equal to 1, right here, we have 20 log K. That is the magnitude of the response. If omega is equal to 10, we are going to have 20 log K minus 20 log of 10, which is 20. Right? So in other words, for omega equal to 10, we have 20 log K minus 20. So what is the difference between those two? In the first case, maybe I should just, let me just clear that a little bit. So for omega equal to, this one is, let me just make it a little bit better here. Put the pen, where? 20 log K when omega equal to 0. Sorry, when omega equal to 1, right? And when omega is equal to 10, we have 20 log k minus 20, right? So the slope or the difference is this point minus that point. Omega has gone from 1 to 10. So the difference in the slope is this minus 20 log k, which is equal to minus 20 decibels. You remember all of these are decibels, right? So in other words, when the frequency increases by 1 decade, the slope decreases by 20. In other words, the slope of this is minus 20 decibels per decade. Everybody seeing that? Yeah? Okay, let's go back over, right? So when we have this equation here for the magnitude response, let me get a slightly different color here. What color can I use? Blue. This is our magnitude response. Let's substitute some values of omega. We know we have a line here, but we want to figure out what the slope of the line is. When omega is 1, we have that this point here, which is omega equal to 1, is 20 log k minus 20 log of 1. Log of 1 is 0. So in other words, when omega is 1, the h of j omega here is just simply 20 log k. Let's go up by a decade. So let omega now be equal to 10. When omega is 10, we have the magnitude of the response is 20 log k minus 20 log of 10. Log of 10 is 1, so this will just be 20 log k minus 20. That's this point here. So what is the slope? The slope is this change over this interval, which is 20 log k minus 20, which is this point. As is the slope, remember, is a decreasing slope. So 20 log k minus 20 minus the starting point, which is just simply 20 log k. So this vertical interval here is minus 20 decibels. And this horizontal interval here is 1 decade, right? 1 decade, right? Because this frequency is 10 times this one. So that therefore this slope is now minus 20 decibels per decade. Yeah? Okay, anybody else not clear on that? Good. And this is the sort of, this is the, well, the English part of it here. So the next slide actually took care of all of that. So that the magnitude plot, therefore, decreases. This is important. Remember, HS is equal to K over S. A pole, a single pole at the origin, the magnitude plot of the frequency response decays or decreases or has a slope of minus 20 decibels per decade. So the straight line approximation, if you like, of the frequency response for this is a line that decreases. So you could draw your magnitude axis, just draw a line, and the slope is minus 20 decibels per decade. Right? What about the phase? Well, we already said the phase, if you go back, if we went back here, the phase is minus 90. It's 1 over j. So the phase angle is minus 90 all over. So HS equal K over S. The phase is a constant minus 90 all the time, because the frequency response to this, it has a 1 over j in it, right, which is minus 90. So let's look at the other one. So that's this second example. So let's look at a transfer function that has a 0 at the origin, k, simply ks. Take the same process again. So the magnitude on phase, we substitute s equal to j omega. We replace s equal to j omega. And we're going to get that this now is, the magnitude is k omega and the angle is plus 90, because we have a j on top here. In decibels, that is 20 log k plus 20 log omega. Notice for the pole, we had minus here. So the slope for this one, h of s equals some ks this time, right? So as simple as 0. This one, the slope, again a straight line, and it increases at 20 dB per decade by the same argument. If you want to do that, when omega is 0, the magnitude is 20 log k. When omega is 10, the magnitude would be 20 log k plus 20. So you could derive this, the same slope is a positive slope. So the zeros increase at 20 dB per decade. The poles decrease, a single pole or a single zero decrease at 20 dB per decade. Yeah? And the phase, because the zero is j, the phase is a constant 90 degrees. Right, plus 90. So we can now expand a little bit. We've had a straight line has a constant magnitude of a straight gain, hs equal to k, has a constant gain at 20 log k, and if the phase is 0, a single pole has a gain that decreases at minus 20 decibels per decade. A single zero has a gain that increases at 20 dB per decade. All right. And let's see, what shall I say? Let's increase the number of the order of the poles now. So instead of this, instead of k over s, we now have k over s to the power n. This could be any number now. So let's increase the number of poles. Same argument as before. You replace s with j omega, so that h j omega is k, the magnitude is k over omega to the power n, and the phase angle is going to be, because when you substitute that here, you're going to have a 1 over j to the n, right? Every 1 over j is a minus 90, so minus 90 to the power n. So if it's 2 minus 180, 3 minus 270, etc. Let's look at the gain equation again. The magnitude equation, express it in decibels, 20 log k minus 20 log omega to the power n, which is n times 20 log of omega. Okay, so you can already see it starts off at 20 log k, but n is a number. So if n is 2, then then this particular bit here, when omega is naught, of course, when omega is 1, this is naught. When omega is 10, 20 log 10, which is 1. We already said when n is 1, which is k over s, it decreases at 20. If you have s squared, n will be 2, so it will decrease at 40. S cubed, it will decrease at 60. S fourth, it will decrease at 80. Right? So you can work it out exactly the same way that we did before. So as you increase the order of if hs is equal to some k over s to the power n, as n increases, the slope of this gets sharper and sharper. It decreases. NS2, it decreases at -20, NS3 decreases at -40, and so we keep going on. And similarly, the phase, remember the angle, it is a 1 over j to the power n is a phase angle. So when n was 1, we had -90. When n is 2, we have -180. When n is 3, we have -270. And when n is 4, we go on to -360. And 360, of course, is right back to where you started off. 360 and 0 is the same thing. So it sort of rotates itself. You can't go past 360. So it will rotate itself back. So after n equal to 4, you're back to 0 again. And so you keep going back down. All right. Everybody following? Any questions? Anything not making sense?
Yes, sir.
Nice. And similarly for the zeros increase. Okay, so the first, same sort of thing, the zeros, the magnitude of the slope increases at n times 20 dB per decade, and the phase increases at multiples of 90 degrees until you reach 360 when you come back down to 0. 360 and 0 are the same things, right? Instead of just keeping increasing, it will just come back down to 0 again. All right, good. So we have all the sort of basic understandings here. So let's start to get now into when we really meet a transfer function that is a little more in line with what we are accustomed seeing. Transfer functions where you have a pole somewhere and you have a 0 somewhere, but they're not at the origin. All right, so we now enter into this, and this is where we really start to produce the full straight line plots. We already know that a constant gives us a line, a single pole gives us a line at -20 dB per decade, and a single 0 gives us a line at +20 dB per decade. So the rest of the lectures here are going to be, well, let's mix and match poles and zeros and see what happens. Okay? So let's look now at a more general transfer function, some p over s plus p. All right, I'm just doing this to make it easy for the time being, but we'll see if you have something different here. So if this was k over s plus p, the approach will be the same thing. But let's start off with the easiest version here. So what is the magnitude and phase response of this? We are drawing straight line approximations here. So let's develop it from this point. So hs is equal to this. I've given you a transfer function. So h j omega will be equal, you replace s with j omega and you get this. The next step, and we'll come to it in a little while, in a few slides down the road, once you replace s equal to j omega, we want to arrange it into this form. So in other words, we want the pole part to be 1 plus something. All right, so as this is p here, we have to divide through by p. So we get 1 plus j omega over p. And well, conveniently, because we picked it that way, we had p on top. So if you divide the top and the bottom by p, you just happen to get a 1 there. It wouldn't make a difference. We'll see later on when you don't have the same constant top and bottom. All right. So step 1, substitute, replace, I should say not substitute, but replace s with j omega. And then you rearrange this form into this 1 over 1 plus j, let's say omega over some constant here. Okay, whatever it turns out to be. And we start to work with this now. So we need to plot the magnitude of this and also the phase of h j omega. All right? And we are using our straight line approximations for this. So let's see what happens now. Let's look at the magnitude of h j omega. Remember this now. If I were to take logs, the magnitude of this in decibels is 20 log to the base 10, understood, of 1, that is this bit here, right? Minus 20 log to the base 10 of 1, right? Plus 20 log omega over p, right? Fair enough? Yes, no, maybe? Just now, let me see, somebody had just now. Christopher, what was that question again? I just saw it there.
So, are you hearing me?
Yes, yes, I am.
So it was with regarding the poles of order. I was just clarifying that the gradients for both more than one and less than one, that the gradients were basically they were proportional to what value of n was.
Correct, correct. The slope is a multiple of 20 n decibels per decade. So once you're plotting it in this form using the Bode plots, for if n, whatever value of n is, right? So you have k over s to the n. If n is, as you just said, if n was -1, then you have ks, which is the 0, and the slope would be plus 20, right? If n is 1 in this case, then you have -20. If n is 2, you have -40. If n was -2, then you have ks squared, which is the 0 instead. So that'll be plus 40, and so you keep going on. Yeah?
Okay, so understood. Thank you.
No problem. And we'll have enough practice. You have we'll have practice doing this way with enough problems both here and in past papers and so on. Okay? Right, so let's look at something now. If I take the h of j omega and convert that, the magnitude of that to decibels, is 20 log of 1 minus 20 log of the denominator here. Look at something now. If omega p, this bit here, if omega over p is much less than 1, then basically h j omega is going to be 1 over 1. And in decibels, 20 log of that is going to be 0. Yeah? Make sense?
So you could explain why, please?
Okay. We're trying to blur, remember what we're trying to do now is to see how this behaves, with frequency. So without, remember the purpose of this whole thing is not to plug in a set of values, but to see if I could use straight lines and the behavior that we just had to predict what the frequency response of this will be. So let's look at something now. I want to draw a plot. Oops, over here. I have h of j omega, and I want to draw the magnitude of h j omega in decibels versus omega, right? So I have this here. So let's see something. If omega over p, if this bit here is much less than 1, in other words, omega, if you look at it, the frequency becoming close to that axis here. Low frequencies, in other words, right? So if omega over p, in other words, this factor is much less than 1, then this whole transfer function basically becomes, if this is much less than 1, this becomes 1 over 1. You with me with that? That makes sense?
Yes, sir.
Right. In other words, and what is that in decibels? 1 over 1, 20 log of 1 is 0, right? So if omega over p is much less than 1, the magnitude of Hj omega is 0. Omega over P much less than 1 basically means that omega is much less than P. Right? Yeah?
Yes, sir.
Make sure. If I'm saying that this bit here is much less than 1, that is this, then just cross multiplying the inequality a little bit, what I'm saying is that omega is much less than P. So if I have whatever P is, remember we're dealing with frequency, let's call this point P here. If omega, therefore, is much less than P, so wherever P is, omega is much less than P, then the magnitude of the response is 0 decibels. So let me draw that. All right. So omega much less than P, this is 0 dB. We all right with that, right?
Yes, sir.
Good. Let's look at the other one now. If omega over P is much greater than 1 now. So omega over P is much greater than 1. Let's see what that gives us now. If omega over P is much greater than 1, then what we have here, if I convert this whole thing to where am I? Get back my pen here. This here, this entire thing is 20 log 1, that's the numerator, minus 20 log 1, that is this here, plus 20 log omega over P. Right? 20 log of 1 is 0. Same way, this 20 log 1 here is also 0. So in other words, this whole thing in terms of decibels is just simply minus 20 log omega over P, which is minus 20 log omega minus 20 log P. Yeah? Calculus, hard maths. Haven't done anything strange here. We all right? Yes, no, maybe? Yeah? Let me know. Good. So now we're looking at the situation. If omega over P is much greater than 1, it means that omega is much greater than P. So we know, if we go back to our line, we're looking at somewhere up this side now. So omega much greater than P. P is somewhere here. When omega was much less than P, we had a line here at 0 dB. Omega much greater than P, so we're up in the high frequency ranges now, right? We have that the frequency response is 20 log of this of course is 0, minus 20 log of omega minus 20 log P. And if omega is much bigger than P, if omega is much bigger than P, then 20 log of omega is going to, as you get very high, 20 log of omega is going to be substantially bigger than 20 log P. In other words, at omega very high, this entire thing really boils down to minus 20 log omega, which is like the behavior of a simple pole that we just had. So at high frequencies now, we know that as the frequency gets high, that the slope is the frequency response is a slope at minus 20 dB per decade. So for omega low, it's a straight line at 0 dB. That's what we had here. For omega much bigger than P, we have a straight line that is sloping at minus 20 dB per decade. So what is the overall frequency response? We join the two lines. This is what we call the asymptotic plot, so that the frequency response is straight line or the asymptotic. You remember an asymptote is just a straight line approximation. ASYMPTOTIC. I hope I spelled it right. Asymptotic plot, right? Right, is going to be for this transfer function is 0 up until P, and once it's greater than P, it decreases at minus 20 dB per decade. Right, which is what we're saying here. Everybody following? Let me know if you need to, if you need me to repeat it. Because this is the key to everything else. After this, once you understand that, then we could handle any transfer function after that, as you'll see.
So could you go over it once more?
Right, okay. So let's see. All right. What's the best way to do this? Okay. Hold on, let me just insert Control M. Good. So here we have a blank thing, right? So I'm giving you Ks is equal to P over S plus P. This next step, to get the frequency response, remember we're trying to approximate the response in straight lines. So we get K J omega, which is equal to P over J omega plus P. And we express this into our form. We want this over the form 1 plus J something. So that to do that, I have to divide the top and bottom by P in this case. So I get J omega over P, and I have 1 on top here. Right, so that's K of J omega. The magnitude of K of J omega, the magnitude of that response, right? You now look at what happens to this response when depending on the value of omega. So let's just draw a little line here and see something. This is K J omega here, and this is omega here. This, of course, is in decibels. Look at something. The first step, if omega over P is much less than 1. Omega over P is much less than 1. This entire thing basically becomes 1 over 1. And in decibels, 20 log of 1 is 0. Make sense? Yeah?
Yes, sir.
Right. If omega over P is much less than 1, what I'm saying is that omega is much less than some value P. So let's put P here. So when omega is much less than P, the magnitude of this is 20 log of 1, which is 0. This is 0 dB. Let's go the other way now. What happens if omega over P is much greater than 1? If omega over P is much greater than 1, then this entire transfer function basically becomes minus 20 log of omega over P. Because remember, it's 20 log of 1 minus 20 log of this entire thing. And if omega over P is much greater than 1, then these two, which is 20 log of 1s, they go out. You're basically left with minus 20 log omega over P, which is minus 20 log omega minus 20 log P. So if omega over P is much greater than 1, that is the area where omega is much greater than P. This is P here. Omega much greater than P is some zone up this side. All right, this is omega. So omega much greater than P is somewhere up here. If omega is much greater than P, it means that as omega gets very large, 20 log of omega becomes significantly larger than 20 log of P. Or this entire response essentially becomes minus 20 log of omega, which is a straight line decaying at minus 20 dB per decade. 20 log of omega, remember, where minus 20 log of omega is like a K over S, which was the first example that we looked at. Yeah?
Yes, sir.
Right. So the two parts, we put the two parts together. Omega much less than P. The plot is, let me just change the color here. Omega less than P, the plot is 0 dB. Omega much greater than P, the plot is minus 20 dB per decade. It's an asymptotic thing, so we're not drawing any curve. So we join the two lines together. They intersect at the point P. Right? So this is the asymptotic plot for the frequency response of a transfer function looking like P over 1 plus 1 over S plus, sorry, for P over S plus P. Right? If the magnitude plot is 0 dB, and then at the point P, it starts to decrease at minus 20 dB per decade. We all right with that?
Yes, sir.
Right. So I'll stop there today, chew that a little bit, and then we're going to come back to this, come tomorrow. That point omega equal to P is what they call the corner frequency or the cutoff or the break frequency for the transfer function. So anytime you see a transfer function, like if I were to give you K of S is equal to 5 over S plus 5, right? You know, when you find it, the frequency response is going to be 1 over 1 plus J omega over 5. The corner frequency here is 5. So for omega much less than 5 in this example, the response is 0 dB. And for omega much greater than 5, it decreases at minus 20 dB per decade. And the two lines, the two straight lines or the two asymptotes intersect at omega equal to 5. All right? Think about it and we'll come back because we're going to meet this and we'll go it over again a little bit tomorrow. And then to see what happens if I don't have this 5, if I have 25 on top and 17 below, what happens, right? You could kind of figure it out already. But you're able to see what the behavior is. So from today's class, what we learned is that a constant has a magnitude response of 0, a line at 0 dB or 20 log, sorry, a constant 20 log K. A single pole is a straight line that decreases at minus 20 dB per decade. A simple 0, which is a 0 that goes through the origin, has a straight line that increases at 20 dB per decade. And then a simple transfer function where the pole is not at the origin is 0 dB up until a particular point called the corner frequency, and then it decreases at minus 20 dB per decade. Yeah? So think carefully about it, and we will continue here tomorrow afternoon when we go on here and we start to handle some slightly more complex ones. Okay? If the denominator is 1 minus j omega with the second half, we will come to that. Yeah? All right. Just now, excuse me.
Okay, no problem. Thank you, sir.
Okay, guys, sorry about that. Right, so we'll take it from here and keep your question. As you look at it, there was a question there about the 1 minus j omega. We will see what that sort of behavior would create, right? If you come up with that issue. Okay. All right. Okay, so until this evening, for some of you all, so let me stop the recording.